2 minutes. No, I don't know, someone left. Can we start? What do you think? Okay, let's start. What I got for today is a frequency and envelope modulated signal. Let's say I have a signal cosine omega 0 time. It's a carrier. It's like an envelope. I would like this carrier to carry my information, which can be, for example, cosine. I will start with very simple cosine omega s time. For the beginning, to make it simple, I will assume that my information is simple one frequency tone. I can add here some P0, beginning phase. I would like to use carrier, I don't know, 100 megahertz signal to transfer my information. For the beginning, I will start with one frequency signal, like this blue line, like this one. See? What I have here? 4 kilohertz. Okay, 4 kilohertz. Let's start with simple. And what's the simple? Signal to call, or you may call it, for example, antenna signal, will be Omax cosine of omega 0 and plus Ks not T. S not T is something to transfer. At the first, hello. I just started. I would like to transfer information as S naught with the help of O maximal cosine omega 0 time plus some Phi0 as a carrier. Frequency and angle modulated signal. I started with the angular modulation. Here I encode or I pack my info in the carrier angle. It will be PM phase modulation. So when the transferable signal is 0, this will be simple carrier. One spectral line. If signal is not 0, we will see deviation in angle, but we also will see deviation in instant frequency. One moment, I will write it. This C not is full phase. Yeah? The thing what's written in square parenthesis is an instant phase. So C naught being omega 0 and plus ES naught can go forward, let's say, or lean, or lag, better use lag. We will see a deviation, delta phi up as Ks max and delta phi down as K modulation depth as min. What's the frequency of signal? idea. One of the way to determine frequency is to take derivative. Here, cosine has an argument of some angle. If we take derivative, we can speak about something called instant frequency. It will be that c in time or omega 0 plus k ds. Instant frequency of angular modulated signal is a derivative of the modulating signal or info I'm transferring. And going the full circle, I can find this cosinus argument as an integral from 0 to time omega. Of course, I need to care about starting angle. Here are formulas for case I'm changing starting phase. I can also play with frequency. I can use frequency to transfer information. How will it look? I will have my instant frequency as some kind of omega 0 plus k s naught. Full phase. Now I'm talking about frequency modulation. Full phase here will be omega 0. Sorry, I should write time here. Omega 0 time plus integrating from 0 to time s plus v0. And I'm able to write the equation for, again, FM signal can be written as O maximum cosine omega 0 time plus k, which is modulation depth from 0 to time plus v0. I am able to introduce deviation, frequency deviation term. Frequency deviation term, actually I can speak on up, it's Ks max, and omega down, it's Ks min. If you compare what I wrote, you see what frequency modulation and angular modulation or phase modulation are very close. In case of small deviations, they are it is not possible to separate them. Okay, what I started with. I would like to at first show simple case with one frequency signal. Let's say I have angle or phase modulation with signal. Let it be sine omega s time. Here I have sine. So, phase will be beta, parameter called modulation index, sine omega st. Beta characterize the, let's say, intensity of angle change. For this case, complete or full phase of my signal will be omega 0 time plus beta sine omega s time. A resulting signal will be cosine of omega 0 time plus beta sin omega s time here instant frequency can be written as, I can get it as x by I'm as a first derivative, so it will be omega 0 plus beta omega s cosine omega s. What do we see? Both phase and instant frequency are subject to harmonic law. Deviation or modulation index beta is delta omega dou x plus omega. There is one moment to see when frequency of my modulating signal changes. In case of angular modulation or phase modulation, frequency deviation will be proportional to my signal frequency. And beta will remain constant. I can write it. It's a small difference. So in case of Pm, beta will remain constant. And delta omega deviation will be beta omega signal. In case of frequency modulation, delta omega will be constant. Deviation, frequency deviation will be constant, but beta will be delta omega divided by omega signal. Now, the most interesting question, spectrum. How do they look like? How do they appear in a frequency space? It's an important thing. Why? Because it determines how much should we pay, what are characteristics of channel we need to order, we need to license from government, to transfer our information. What quality of cable we need to buy if it will be cable line, and so on. PM. What was the formula? O max cosine omega 0 time plus beta sine omega st. Here is my single tone signal. I can rewrite this. 1 second, I will rewrite this in a specific form. I can rewrite it as O maximum cosine beta sine omega s minus sine of beta sine omega s time. One more. Yeah, now it's okay. Here is my formula for angular modulated signal. It's not one easy to use. To make it clear, I can assume very small bets. Very small modulation index. In case of very small modulation index, it's ineffective. Such use of communication channel is not effective, but as a teaching example, it will work. If I assume very small betas, cosine beta sine omega s time can be approximately assumed equal to 1. And sine of beta sinus omega s can be approximately substituted with beta sine omega 0 it's a very approximate substitution, but for the first step it's okay. So at first approach I'll be able to write my signal as O max multiplied by cosine omega 0 time plus beta by half multiplied by cosine of omega 0 plus omega s multiplied by time. Minus beta by half cosine of omega 0 minus omega s time this one closes and this one closes. So, what do we see? Something familiar? No? Take a look. Component 1. Omega 0. Contains information? No, it has 0 information. Component 2. Omega 0 plus omega. And component 3, omega 0 minus omega. What do we see? Something familiar. Amplitude modulated signal. Looks very similar, but with one only exception. When we have very small depths of modulation, we will get something similar to amplitude modulated signal, but with inverted LSB. It's an LSB part. Here we will have inversion. The same you will see for frequency modulated signal. You will get something if you have one key moment. You need to have it's true when you consider small betas. Higher beta, more effective use of carrier means what you will get something different. But at the first approach, you will get something similar to amplitude modulated signal, but with inverted LSB. You can take AM signal, invert one of the sidebands, and it will become a frequency modulated signal. Sorry. Signal. Oh, yeah. One moment. I'll get my signal. One moment. I need wire. let's take a look what I got here. I have signal at this moment. Okay, this one. It's a 2 kilohertz signal. And this 2 kilohertz signal is used to amplitude modulate 32 kilohertz signal. This generator now has omega 0. So omega 0 is double P hertz, and omega is 2 kilohertz. Blue line is a modulating signal, and yellow line modulated. And what on the red line? What about my red line? Oh, here is my red line. What's the central frequency? Don't like it. I'll tell you what's going on. The problem is that 32 megahertz is too high for my scope. I'm using this receiver with its, because I have access to interim frequency. I use this receiver to transfer from real 32 megahertz to the lower 4 megahertz frequency. And this one, this yellow line, is a 2 megahertz signal transferred to 4 megahertz. So it's a bit different. We see signal at interim frequency. It's a bit changed. Oh, and I know why. Because I used this way better. I used a narrow filter on the interim. Now it's better. This way better. It's nice and symmetrical. Now, anyway, where is my come here? My signal at amplitude modulated. Bit strange, why? I don't know why. I should see mirror of this one. Okay, can I get deeper modulation? Not deep enough. Can I get deeper? another wire. Internal source is more powerful. Actually, I need small index. To make things, say, clear. Second harmonic. Come on. Okay, K is central frequency and sidebands. You see now amplitude modulation. I will switch back to the small indexes. I need Here is my signal I'm using for amplitude modulation. Central frequency, one sideband. Should be second one. Receiver bit asymmetric. What I'm waiting for? I need to switch that. So, now you see 32 megahertz modulated with 2 kilohertz, amplitude modulation. Oh. Very, very small. Modulation depth. Very, very small band. Something about couple percent. Here is very small band. You see difference. Amplitude modulated. Frequency modulated with small band. The same. Because here only absolute values of frequency are drawn. You don't see this band inversion. But what will happen if I increase this one, this usage is ineffective. If I would like to get more effective usage of frequency band, I'll need to increase depth of modulation. When you will need a mass description for result, you need to open your mass book and found Bessel function. Can be decomposed as O max sum where k from minus infinity to infinity, Bessel function of k order multiplied by cosine of omega 0 plus k omega s time here take m equal to beta. You will need a Bessel function of k order. In reality, here is a reaction to the modulation depth increase. First appears double, then triple, quadruple, and going forward, one second, I will change scale to make it more visible. Very small modulation depth, going deeper, deeper, deeper. One moment, I will switch to internal. Here I have frequency deviation 75 kilohertz. To make it one moment. Zero frequency deviation 5 kilohertz, frequency deviation 10 kilohertz, frequency deviation 15 kilohertz, and here at the end, frequency deviation 75 kilohertz. What do we see? Spectrum goes wider in both sides. Practical, it will be approximately, this size will be approximately double P plus 1 omega s. It's what realistic. Wait one moment, I'll show one more thing. Here I'm using one frequency signal, one tone. What will be for more complex? Again, returning to amplitude modulated single frequency. AM signal single frequency. What signal? Familiar something? Rectangles. And what about spectrum? My modulating signal now has spectrum like something like 4e divided by t sine omega st plus 1/3 sine triple omega st plus 1/5 sine of 5 omega st. Free frequency. How can I get them better? I'm in AM mode, and in AM mode you can see wait one moment, let's try to book. Let's set this to 0 and red line. Why it's saying 90? It's lying. Okay, it's omega s as it thinks. No, it's a, sorry. It should be I'm above Nyquist frequency. My problem, I'm above Nyquist frequency. Maybe. This way it will be able to show me better. Oh, come here. You come here. Okay, I have a bit. No, this is not better. Again, I see this stupid. My problem, I want too much from the scope. Okay, anyway. Central frequency and omega signal, small triple omega signal, and small 5 omegas. It's max I can get. No, it's not for everyone. Okay, now I see amplitude modulated signal. Frequency modulated signal. Zero modulation depth. Frequency deviation. 1 kilohertz. Frequency deviation 3 kilohertz. Maybe I can. I should multiply. Yeah. Recalculate. Come on. Oh, this should be, yeah. See what's going on? Not only signal, it's harmonics and all multiplication of all harmonics. Without higher components, with higher components. Without, without quite complex thing. Maybe I can take a look on something more complex. This signal is a test. It's a very simple signal. How real? Can I take a look on real? Maybe not. I need something more realistic. Something more realistic. Can I get something more realistic? Oh, I see. Okay, stop crying. Okay, real broadcasting station. Nice. At interim frequency, what do we see? Carrier and something around. Looks like not a very deep modulation. Now I'll switch to the modulated signal. Come on. Here is the modulated signal. Some kind of sound. And what in frequency space? Compressor. Oh, it's a lot of more compression. Something black. I will take your special price. Okay, do not disturb me. Let's take a look on the real broadcasting FM signal. See frequency. 1, 2, 4, 5, 6, 7, 8, 12, 13. It's the limit of the human's hearing, yeah? They are transferring. They are transferring this near sports shop advertisement. Oops. Ooh. 19 kilohertz. Why should someone transfer something on 19 kilohertz? No one hears it. How can I compress more? And amplitude. What about, I'm interested in this area, 38. This part is a sound, it's clear. And what's that? Where my cursor stands. You see? Sporadically appears something like picture like this. 19 kilohertz. Something like sound here, and at 38 kilohertz. Something appearing like, take a closer look at this area. It's periodic when scope calculates, signal appears. The trick is, this radio transfers stereo sound. Means what you need to put right channel and left channel. This trick is called Zenith system. Idea: at lower hearable frequency spectrum part, they transfer A plus B or left plus right. It's a mono signal. For receiver to extract stereo from this, at 38 kilohertz, A minus B, or left minus right, is transferred. But there is a problem. It's with spectrum transfer, left minus right can be easily sent to this 38 kilohertz. But there will be a problem. Central carrier will remain, disturbing TV sound. That's why carrier is suppressed. You don't have 38 kilohertz. My red line cursor stands on point where it should be, but it's not there. It can be balanced modulated signal, can be easily demodulated, supplied by central from the local heterodyne. What I show with this nice old receiver. There is one tiny problem. Even small shift in frequencies between original carrier and local heterodyne means what you will get serious sound distortion. To prevent this shift, at 19 kilohertz, so-called pilot tone is transmitted. It's a signal for local heterodyne needed to extract this left minus right or A minus B signal correctly. Yes, 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 yes. And that's not all. Second harmonic of the pilot tone, maybe I can strangely the station don't have a large difference between left and right. Maybe I can find someone. Very strong pilot. See, it appears periodical. Scope I calculate slowly. That's why it appears like a flash. And that's not all. I need one more point. It's a 50. A should be here. No, only noises. I'm seeking for the third harmonic of the pilot tone. It's a bit shift. This one will work. This one will work. Nice pilot tone. See, 57.3. Actually, I need 58. I need this. You see? Two small pillars around my cursor. It's FDS. It's a data channel transmitting station name. It also can broadcast emergency information and even maps. When in your car you switch FM radio, you see its name. Actually, this name at around 58 kilohertz with quite sophisticated encoding, station name is transferred. And here, see, another thing. 75.8. This should be business information. I don't know, is it possible to subscribe? It should be 58, but appears what central is 57. They have days broken, Oh, my scope is broken. Left minus right. This area, left plus right, monophonic C. Pilot tone, going forward. Up. Look how nice. Left minus right, transfer to 38 kilohertz. And I cut it off, well, it will be FDS signal. Funny word of FM signals. Okay. The modulation, one more moment, how can I extract my signal? Simplest way is with the frequency discriminator. Take a resonant contour with offset. Its F0 should be selected, so the omega 0 will be on a side slope of characteristic. Come on. This means what if you have omega, I don't know, like this. This is frequency, this is time. Result will be an amplitude modulated signal. It's called frequency discriminator. But frequency discriminator is not the best. It's okay for voice, but it's not okay for quality sound. For quality sound, if you are interested, ask Google for related detector, or also a technique based on a Hilbert transfer, where frequency modulated signal is multiplied with latitude signal with same frequency and quadrupole with a phase shift of 90 degrees. Result will contain what you're looking for. Okay, relation detector called this thing. I'm looking for. Here I can, and I'm looking for attendance chart, isn't it? Or maybe show something more complex. Who would like to see more complex signal? Really, you can combine amplitude modulation and frequency modulation, or angular. More often, angular and amplitude are combined. In its basic form, it allows you to transfer two signals simultaneously. It's quadrature modulation, where angle is one signal and amplitude is second. Why should someone need to transfer two signals for data? QAM, quadrature amplitude modulation. Draw borders. Make this, for example, 0, 0, 0, 1. 1, 0, 1, 1. Okay. More. 0, 0. This first version will be 0, 0, 1, 0, 0, 1, 1, 1. Basic version. Its inner can be achieved with the phase modulation. Now if you add amplitude, you will have one more bit. I mean draw it. 0, 0, this will be 0, 0, 0, 0, 0, 1. 1, 0, 1, 0. So here is 0, here is 1. Here 1, 1, 0, 1, 1, 1, and 0, 0, 1, 1. Triple, I have triple bits with amplitude. More. Add more border and you will have qubit. This will allow you to transfer 4 bits at one cycle. If you go to the extreme, you will see so-called constellations. What can you do? This also doubles data capacity, yeah? Better use angular gradation than amplitude, but easily use zonal structure like this, and you can transfer. QAM 64 is nothing special. 64 bits, 8-1 peak. Go further and you will have trellis coding. Trellis coding operates with so-called constellation where you don't have a sector like this, but kind of area. And one moment with the trellis. Trellis is like a back. It has concave edge to compensate disturbances by communication channel. TQM, trellis encoding. But TQM was on top phone line modem. Today channels are better and so people prefer quadrature modulation. Trellis is more this fight with constellation is no longer popular. Your TV decoder, well, you don't have TV decoder. Mobile communication, QAM 64, even 128. Okay.